After discussing Bloch theorem, let's try to find out the energy levels of electrons in a periodic array of quantum wells. So that is a possible a simple kind of potential for which we have in quantum mechanics course learned the solution. We know what kind of wave function we have for the potential wells. So we will try to work this out to understand what exactly happens if we put an electron in a periodic potential. And in order to do this, we will first take something very simple in hand, and then we will further simplify it to understand the idea, and we will apply Bloch theorem to find out some reasonable solution to this problem. So how do we find out the energy levels for a periodic array of quantum wells? Let's draw the picture first. Say we have this kind of a quantum well, this kind of a barrier, again a quantum well and a barrier, and a well, a barrier, a well, and this keeps on extending on both sides. It doesn't end anywhere. Now let's consider this as the x-axis, this is x, and let's consider this as the potential axis, Vx, and if we put x equals 0 here, then here x equals minus w, that is the width of the well is w. Here x equals b, the width of the barrier is b. Here x equals b plus w, and so on. The potential is 0 here and is V naught here. So the lattice constant for this kind of an arrangement would be A equals W plus B. This is the lattice constant. A is the lattice constant. Now, if we consider an electron within the unit cell, then the unit cell ranges between minus W less than X less than B. So within the unit cell we have the well region, this region, that is minus W less than X less than 0, let's call it region 1, and then there is the region 0 less than X less than B, this is the barrier region, and let's call this barrier region as region 2. So, we know the general solution for wave function in region 1 and region 2 from our quantum mechanics courses. And if we have an electron or any quantum particle with energy more than 0 but less than V0, we will have an oscillatory solution in region 1 and an exponentially decaying solution in region 2. This kind of a solution will be there. So, the solution for wave function for region 1 can be expressed as A e power I qx plus B e power minus I qx. This is for the region minus w less than x less than 0 and q, which is a function of the energy, is twice me over h cross squared square root of this quantity. In region 2, that is the barrier region where the energy of the electron is less than the barrier, here we won't have e power I kind of a thing, which is the signature of an oscillatory solution. We will have rather exponentially decaying solution e power c e power beta x plus d e power minus beta x. This kind of a solution we will have. This is in the region 0 less than x less than b, and here this beta, which is a function of energy, may be expressed as twice m V0 minus E over h cross squared and square root of this quantity. So, we have learned this in the quantum mechanics course. We have just written the solution, the general solution here, and let's see what it means. So, this quantity QE, this is the propagation wave number in the well, and beta E, this refers to the barrier. A, B, C, D, these are arbitrary constants so far. We consider E less than V0, and so the arbitrary constants must be chosen in such a way that the boundary conditions are satisfied. What are the boundary conditions? We must have continuity of the wave function and the continuity of the first order derivative of the wave function in space, so that the wave function is differentiable to at least the second order. So, those are the boundary conditions that has to be obeyed, which has to be observed at x equals 0, which means we have the boundary conditions psi 1 0 equals psi 2 0 and d psi 1 dx at x equals 0 equals d psi 2 dx at x equals 0. Is there another non-trivial point? Yes, there are other non-trivial points to be considered. For a periodic boundary condition, we will consider that this point here, that is this x equals b, and this point here, that is this x equals minus w, these are equivalent. Because they are equivalent, we will also have psi 2 at b equals e power I k a psi 1 at minus w. So, this factor e power I k a comes from the expression of the Bloch theorem, this form. This form gives that kind of an expression, and the other condition for the derivative would be d psi 2 dx at x equals b equal to e power I k a d psi 1 dx at x equals minus w. The condition here on this line imposes the continuity of the wave function and its derivative at x equals 0, and the second condition, that is this one here, that comes from the periodic boundary condition. The phase factor e power I k a is required by the Bloch theorem, as we have discussed. So, now these conditions lead to the constraints or the equations of the arbitrary constants that we have. From these conditions, we find a plus b equals c plus d. We get a times iq minus b times iq equals c beta minus d beta. C times e power beta b plus d times e power minus beta b equals e power I k a times a e power minus I q w plus b e power I q w, and finally c beta e power beta b minus d beta e power minus beta b. This quantity equals e power I k a times a I q e power minus I q w minus b I q e power I q w. So, we have a set of 4 equations with 4 unknowns in here, and in order to have non-trivial solution for all the unknowns, we must have the determinant of the coefficients of a, b, c, d to be equal to 0. That is the condition for solving set of linear equations. So, we must have the coefficients, that is 1, 1, minus 1, minus 1, iq, minus iq, minus beta, beta, minus e power I k a minus I q w minus e power I k a plus I q w e power beta b e power minus beta b and minus iq e power I k a minus iqw iq e power I k a plus iqw beta e power beta b minus beta e power minus beta b. This determinant must be equal to 0 in order to have a non-trivial solution to the set of equations. And if we set this determinant to 0, we will arrive at the following condition: beta squared minus q squared over twice q beta sine hyperbolic beta b times sine qw plus cosine hyperbolic beta b cosine of qw. This equals cosine of ka. This kind of a condition we arrive at. Now, if we make a simplification, that means we change the form of this barrier a little bit without really changing the problem too much, just for simplicity. We make the following simplification. We make the width of the potential barrier approach 0. That means B tends to 0. And we have a periodic sequence of delta-like, Dirac delta-like potential barriers where B tends to 0, but V naught B, this is a constant. That means integration over the Dirac delta will give us V naught B. So these are the constraints that we apply on the problem, on the pattern of the potential barrier. So with this we obtain a simplified solution which is P times sine QA over QA plus cosine of QA equals cosine of KA. What is P in here? P is M V naught B A over H cross squared, and this is a dimensionless parameter. It of course depends on the materials properties. The V naught is there, A is there, these are the material dependent quantities. Now, if we try to plot this equation and obtain a graphical solution to this equation, what do we get? Let's plot a quantity f, that's a function of QA, which is given as the left hand side, P times sine QA over QA plus cos QA. So we are plotting FQA, f as a function of QA in the y axis, and in the x axis we are plotting QA. What kind of graph shall we get? We will get something like this. Which will keep on going. Now let's consider something interesting here. This quantity has to be equal to cos Ka, cosine of Ka, which ranges between -1 to +1. Say -1 is here and +1 is here, then the acceptable solution, acceptable values of Fa that makes sense is confined within this region. Which leads to a gap here. There is no acceptable solution. A gap in this region, there is no acceptable solution. A gap here, a gap here, and so on. So if we move higher on QA, there would be smaller gaps, and once after certain value there would be no gap. The gap will not exist anymore. But at lower values of QA there are gaps in this spectrum, and we can see that if P, this value of P becomes 0, then we will have perfect free electron, and if P tends to infinity, if P is very large, then we will have a very narrow band in here, very narrow region where acceptable energies are possible. Beyond that it's not acceptable. And in general, for moderate values of P, the energy spectrum would be gapped. Not every energy would be acceptable for the energy of the electron under consideration, which is subject to a periodic potential. So when we have the electron in a periodic potential like this, it will not have any arbitrary energy. It cannot have any arbitrary energy. Rather, there are certain energies that are forbidden. This is what we learn from this mathematics, this kind of simple model that we have considered. Certain energies are forbidden. This actually gives the idea of band gap, and this model is known as the Kronig-Penny model.